In this example, we are going to analyze the critical components of the frame that we have here. The critical components are member BD and the pin at C. In the part A, we have to estimate the required thickness of the member BD to avoid yielding failure with a safety factor of 3. In the part B, we have to estimate the required diameter of the pin C to avoid ultimate shear failure with a safety factor of 3. We can also find here the different data that we need to solve this problem. Let's start with the free body diagram of the member AC. Then we have here the applied load P, and then we have here the reaction force in the x direction of C and the reaction force in the y direction of C, and we have also here the axial load FB, which we can split into two components, one in the x direction and the other one in the y direction. We have also here this angle that I will call theta, and then we can calculate what is the tangent of theta, that is equal to h over L over 2, which is equal to 4 over 3. We also need the sine of theta, like we can compute, and we find that is equal to 4 over 5. Now we can find Cx if we sum the forces in the x direction, then we can find Fbx minus Cx equal to 0. Then we find that Cx is equal to Fbx. And now we can sum the moment at the point C, and then we can find that that P times L that is negative, plus f by times L over 2 is equal to 0. Then we can find that f by is equal to twice p times L over L. We can cancel this, and then we find that f by is equal to 2 times p. Now we can find f bx using the tangent. Tangent of theta is equal to f by over f bx. Then we have f bx equal to f by over over tangent of theta. We know that the tangent of theta is equal to 4 over 3. Then we have that f bx is equal to 3 times f by over 4. Now we can find fb using sine of theta. Sine of theta is equal to f by over fb. We know that fby is equal to 2p, and we also know that sine of theta is equal to 4 over 5. Then we have that fb is equal to 2p over 4 over 5. Then we find that fb is equal to 10 times p over 4. Then we can simplify and get fb is equal to 5 times p over 2. Now we have fb. We can find cy if we sum the forces in the y direction. Then we have sum the forces in the y direction equal to 0, and we have minus b, we have plus f by, and finally minus cy equal to 0. Then we have cy is equal to fby minus p. Well, we know that fby is equal to 2 times p, and we can find that cy is equal to 2 times p minus p, which yield cy is equal to p. Now we can calculate the axial stress in the member BD. Then we have that the axial stress is equal in the member BD is equal to force FB over area. We know that the area is equal to B times T. B times T, because it's a rectangular cross section. So if we have, this is T and this is B, this is the cross section. Then we find that sigma in the member BD is equal to 5 times P over 2 times B times T. Now we know that the safety factor is equal to the yield strength, that is sigma y, and is a material property, over the sigma applied, that in this case is sigma BD. Then we know here that the safety factor is equal to 3. Then we have 3 equal to sigma y over 5 times P over 2 times B times T. Then we find that the thickness of the member BD is equal to P 6 times P over 5 times B times sigma y. Then we have the solution for the part A.